So, torques with what? Did I say angles? Everybody? We're going to be doing components. Suppose we have a situation as follows. The beam below has a mass of 12 kilograms. Total length is 8.5 meters. What's the total length here, Jeremy? And since that's 0.5, I'm guessing this is 8. I can do that in my head. I'll remember that. If the beam is in equilibrium, this is key. That means the beam is neither accelerating nor spinning. What's the tension in the rope? When I used to cover this on the provincial, I would say, you know what this is a good job for? Everybody. This is a free body diagram. It's going to be a pretty complicated free body diagram. It's going to start out okay and then get pretty challenging. But let's go systematically. Get the obvious one. What are the forces acting on this beam? Its own weight. Where am I going to put that? Center of mass, Cormac. You with me, Cormac? Can you look up and sit up? Thank you. And I drew further through the ground because, Carson, it's a clever trick. I noticed that gave me a right angle. It gave me a triangle, which I thought that might come in handy to move angles around. If you're taking upper level physics next year, a handy trick is if they happen to give you a vertical or a horizontal line and you're doing a diagram, extend your line through it. It almost always helps. Okay. The beam is at an angle. Because there's angles, I'm going to break gravity into components. I'm going to break gravity into its parallel and perpendicular components. I'm going to go like this. D, 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 D. This is going to be, I'm going to call this, since there's only one object here, I'm just going to use mg. If there was more than one object, I would use mb for beam. So I can call this mg. This is the perpendicular component. And mg, here's the parallel component. Here's the 90. Sean, my friend, how big is this angle right here? How big is this angle right here? 90. So how big is this angle? How can I figure out how big this angle right here is? Anyone? If this is 35, that's 90. How can I figure out this one? 90 minus 35, which is what? 55, you say? How big is this one? Well, what do these two add to? 90. So how big is this little angle right here? 35, 90, 55. How big? 35. Now, what we did, this is a review. We actually derived this way back in November. For ramps, I went color, 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 color. We did that. But I just quickly re-derived it because I had a feeling you might have forgotten. But it comes out of, hey, if that's 35, that's 90, that right there is 55, these two add to 90, 35. Okay. What else? What other forces are acting on this beam? There's another fairly obvious one just because of the picture. Yeah, what are we going to call that? Starts with the letter T. Yeah, tension. So I'm going to just say, okay, here's tension like this, and I'll put a T there. Tension is also at an angle. Did I say angle? Components. I'm going to break it up into a perpendicular component. Put the arrows on the end. Those help. Make it a fairly big triangle. That helps. And then a parallel component. Tension, parallel. We're going to do a similar dance, Nathan. Nathan, how big is this angle right here? How big is this angle? What do these two form together? A 90. So how big is this angle? How big is this angle? If that's 90 and if this is 50, it's also 40. Now, why did we do that? It's traditional if they give you a 40 to use the 40. I have no problem if you just use the 50 right there. But typically in my answer keys, oh, they gave me a 40. I'll find where the 40 is in my diagram. Had they given me the 50, I would have found where the 50 was in my triangle. Okay. So what else? There has to be other forces. Yeah, what's your question? Right there? How big? How big? How big? 50. How big? 40. You said it. By the way, you're at a disadvantage, all of you. When I was back when this was in the back when there was a provincial exam, we used to do a geometry in Math 12, and so the kids would all have learned that if you had a Z, the interior angles of the Z, whether the Z is forwards or backwards, we called these alternate interior angles, and they were the same. Kids would have just glanced at that, or some people called them Zangles, was a stupid way to remember it because of the Z. They would have said those two angles are the same, but we have to walk through it by hopscotching. Okay. This can't be it. I'm going to draw a bunch on here, but look up. Don't write this down. I'm going to muck up my diagram. Look at tension. The other way I could have broken tension up, don't do this, but I could have broken tension up into horizontal and vertical. Don't write that down. What direction is the horizontal section of tension? I'm looking for a word that starts the letter L. Are there any forces pointing to the right? Then this can't be an equilibrium, or we're missing some forces, and we are missing some forces. What do you think is pushing to the right on this beam? It's not obvious. If you don't get it, don't feel bad. But there's somewhere we've kind of ignored that can also be applying a force. I don't know what that means. You're correct. You're talking here? Okay? The pivot is applying a force. We'll call that the pivot. Okay, you call it a fulcrum. The only reason I don't use the word fulcrum, you already had F fulcrum, F field, F force. It was too many words to get mixed up. So I went with pivot, which is also considered acceptable. So because of this, you can add that. There we go. You can add, I'm going to call it a horizontal force. And I can even tell you how big it is. It's this magnitude of the horizontal component of tension if I had chosen to find that. There's one more force as well. Somebody said it, actually. Yeah, this object is sitting on the ground. I'm just going to call it an Fy because it's not a nice normal force that I can say to you, oh, but look. I do know the ground has to be pushing up vertically, but if I had a vertical component of tension, it's canceling out some of this mg, but it's complicated. Okay. That's the free body diagram in blue. I should, just so you can see that this is part of it. Tension, mg, fy, fx. The ones that are at angles to the beam I found components for. Carson, why didn't I bother finding components for fy and fx? They're not parallel. Patience. Is there a beam in this? Oh, you were away, Carson. Sean, you were away. I got to move somebody else. Maya, is there a beam in this question? Say yes. We're going to use torques, and the smartest place to put the pivot would be draw this in right there. Why would I put it right there? Who remembers from yesterday? Torque was equal to what times what? Force times perpendicular distance. Maya, how far is Fy from this pivot exactly as a number? How much torque will it exert then? We can ignore it. How far is Fx exactly from this pivot as a number? 0. How much torque will it exert then? 0. That's why we put the pivot there. We had two forces we didn't know. Who cares? All right. They want me to find the tension. I'm going to solve this with torques. Why torques? Because there's a beam. The first thing I'm going to write is the sum of all the torques clockwise, that's in this direction, equals the sum of all the torques counterclockwise, that's in this direction. So now we're going to have to use our imagination. This part, Carson, you can try. We're imagining that things can pivot right here. Imagine the ground isn't there, that it's just kind of stuck, that pivot is stuck there. Which force, perpendicular force, please, would cause the beam to spin clockwise? Now, clockwise is in this direction. If you're not sure, I used to actually have my kids hover their pencil above their paper and draw the circle like I'm doing with the eraser. So I would say, okay, clockwise, clockwise. Carson, can you see which force is going to cause this beam to spin clockwise? Yes. But it's force times perpendicular what? So mg perpendicular times its distance from the pivot. How far is it from the pivot? Half, how long is the beam? Beam is not 8. Read carefully. How long? 8.5. So it's going to be halfway. Yeah, we can probably do that math on our head. 4.25. That's the clockwise torque. Carson, back to you. Which force or forces is exerting a counterclockwise torque, causing it to spin in this direction? Perpendicular tension. Good. Times its distance from the pivot. 8, because 8.5, 0.5 from the end, 8. Pause for a second. Let's do the components. mg perpendicular, we can use the shortcut that we had for all of the forces that we did, because this looks to me like a ramp. So we had 2 lines was sine. Which trig function was perpendicular? Of course it was. So we can say this. It's going to be mg cos 35, and then the 4.25 drops down like a domino. And over on the right-hand side, I mean, the 8's going to drop down like a domino. I need to get an expression for the perpendicular component of tension. This one, unfortunately, is a little bit trickier. I'm going to go color, 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 color. Tension perpendicular, opposite, adjacent, or hypotenuse? Try the third one. It's opposite. Tension, hypotenuse. I don't care about the parallel ones. I didn't even bother labeling it. Which trig function has the O and the H? Which trig function has the O and the H? Sine does. So we're going to have sine of 40 equals opposite perpendicular over tension. We want an expression for perpendicular. We want to get the perpendicular by itself. How would I move this t over? So I'm going to go boom, boom. What can I replace the perpendicular component with? T sine. What can I replace the perpendicular component with? T sine 40, having to write small. I don't know if you remember, I said I kind of like these questions because this has been a lot of work to get here. But then at the end, there was always kind of a, because Nathan, what were they asking me to find? Get the t by itself. How would I move the sine 40 and the 8 over? And you kind of end like, oh, that was kind of anticlimactic. After all that setup, oh, I can get that by itself. Yeah, you want to know what the tension's going to be? I'm going to move down a whole line. Tension is going to be mg cos 35 times 4.25. You said, yeah, divide by the sine of 40 and divide by the 0.8. So it's a lot of setup, Sean, but at the end you kind of, not too bad. And that's really torques with angles. We're going to do one more ugly one and then we'll call it. Yeah, crunch numbers, what do you get? I think they gave you the mass of the beam, G 9.8. I'm not doing this one in my head. I think you get something in the 70s, but don't quote me on that. I'm going from memory and I could be totally wrong. One of our answers, I think, was in the 70s, but maybe it was not this one. No, is this, no, what'd you get, Carson? 22.8? I don't think that's right. Is that right? Okay, let's type. Put the bottom in brackets. On the top, 12, was it 12 kilograms? Times 9.8. Cos 35 times 4.25. Close off the top. Divided by bracket sine 40 times 0.8. I made a typo here, didn't I? Sure I did. Not 0.8, it was 8, Mr. Dueck. I don't know why I dropped a point. It's an 8. I don't know why I put a 0.8 there, folks. 79.6? Yeah. Okay. Where would you be using this? You can imagine over here a crane. This is the crane. This is the, well, you know what? I can show you a picture. Something like this. This is where you might have a crane with a weight on the end of it trying to lift something up. And you always have a cable running from what's called the beam or the gantry of the crane back to the machinery to raise things up or down. You could actually calculate how much force do I need to exert through that machine to lift up the beam or not. In fact, here's what I said. There are two main types of beam problems. Forces on a beam when the beam is horizontal, those are easier. Tougher, forces on the beam when the beam is at an angle and the rope is at an angle. Did I say angle? Components. Let's zoom into here and let's just do the free body diagram. What are the forces acting on this? Get the obvious one. And since there's a load as well, I'm going to put mass of the beam times G, and mass of the load times G. I'll use L for load. Come to that. Definitely tension. Now, tension is at an angle. Did I say angle? I would break it up into tension perpendicular, tension parallel, and color, 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 color. For what it's worth, there's the Z. If this was all there was, this beam could not be in equilibrium because tension is pulling in two ways. One way that tension is pulling starts with the letter U, Sean. One way that tension is pulling starts with the letter U. One way that tension is pulling starts with the letter L. Okay? I mean, up maybe is canceled out by these two, but is there anything canceling out this arrow pointing to the left? I must be missing a force. Where are we getting a force from the right? Wall is applying a horizontal force this way. I usually just label that Fx because I didn't know what else to call it. It's kind of a normal force, but not really. Usually the normal force is in response to gravity, and this is not being caused by gravity. That's not all. The wall is also lifting up like that. And the way I know that is if this was just pressing against there, this would just flop down, clump, like it would fall. There's nothing holding that up. So the pivot is doing two things. It's lifting up part of the beam and the mass from that end, and it's applying a force outwards from the wall. Really, really similar here, but more angles. What are the forces acting on the beam? Get the obvious one. So we would have mass of the beam times gravity at an angle. Did I say angle? So we would have mass, beam, gravity, perpendicular, mass, beam, gravity, parallel. And for what it's worth, this angle and this angle would be the same. Now we're going to kind of overlap a bit, unfortunately. So we're going to have right here, here's mass of the load G at an angle. Sean, did I say angle? You awake? You awake? You doing good? Because you're leaning further and further back. Okay. And this would be mass of the load G perpendicular, mass of the load G parallel, and also that angle would be the same as that angle would be the same as that angle. Then we would have tension at an angle. Did I say angle? we would have a perpendicular component of tension, and we would have a parallel to the beam component of tension. And for what it's worth, this angle and this angle, I'll use check marks. I used X's for the other ones. Those two angles would be the same. And then the wall is doing two more things. It's exerting a vertical force and it's exerting a horizontal force. How do I know those are there? It's not as intuitive as the previous one, but if you actually put in legit numbers that work, you'll find they have to be there. Otherwise, things don't balance. Otherwise, you have unbalanced forces, which means this would be accelerating and is not. Let's do one together of this first type where the beam is horizontal. That's where I'm going to hit pause. So I said to solve beam problems, we are going to apply the two conditions for equilibrium, which means the forces equal zero, all the forces up equal all the forces down, all the forces left equal all the forces right, and the sum of the clockwise torques has to equal the sum of the counterclockwise torques. If there's a beam, I tend to start with torques, and I tend to put the pivot where the two unknown wall forces are, because that means they exert no torque. Here's one with numbers. We'll finish with this. It says find the chord tension. I'm going to call that part A, and then find the hinge force. I'm going to call that part B. Cooper, how am I going to start? What are we going to call that now that you're not staring down at something? This is a good job for you. Okay, you back with me? Okay, I'm going to zoom in so you can see. I think the first thing that I would say is get the obvious one. Whoop. Let's try that again. Let me write. There we go. Mass of the beam times G. Do I need to put this one into components? No, because the beam is horizontal. What else? Cormac, what's on the very end of this beam? So there's also going to be right there mass of the load times G. Okay. What else? Tension. So I'll make a little note. There's tension right there. Tension is at an angle. Did I say angle? We're going to do components. I'm going to have tension perpendicular, tension parallel. You can draw that triangle bigger if you want and over. I just wouldn't draw it much smaller because it's handy to be able to draw in here. And, oh, color, color, color. There's the Z. Color, color, color. By the way, which way is tension parallel applying a force? I'm looking for a word that starts with the letter L. Left. For this to be an equilibrium, there has to be some forces pointing right. Are there any forces pointing right now? So that's how I know, you know what? There's a horizontal force right there. And also, trust me, there's a vertical force right there. That's what they want me to find in part B. But for part A, I'm going to use torques. Are we spinning? So what we said last day was we can say the sum of all the clockwise torques, and I draw an arrow like that, has to equal the sum of all the counterclockwise torques, arrow in the opposite direction. Clockwise, if that's the pivot, is in this direction. Davin, which force or forces would cause this beam to spin clockwise if they could? Nope.
Clockwise.
Clockwise. That's why I'm going like this, dude. And the other M, like MB, both the gravities. Okay. So how do I calculate torque? Torque is force times perpendicular distance, or perpendicular force times distance. So it's going to be this, the mass of the beam times G times how far is the center of mass from the pivot? It's a good question. Cooper, how long did they say the beam was? They told me in the question. So half of that, 0.41, I can do that in my head. And mass of the load times G times how far is it from the pivot? Oh, it's on the very end of the beam, 0.82. Those are my clockwise torques. That has to equal, okay, what's going to cause this to spin counterclockwise if it could? Only tension perpendicular times its distance from the pivot. Oh, is it also at the end of the beam? Also 0.82. Now I need to do some trig. I need to get an expression for the perpendicular component of tension. So I'll zoom in, I'll zoom out again in a second. I already did color, 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 color. Okay, tension perpendicular, opposite, adjacent, or hypotenuse. Davin. Redeem yourself, dude. It's opposite. What about tension? It's opposite. That's why we color, color, color. Opposite. Dude. And this is hypotenuse. I don't care about the parallel component because I'm not going to use it at this point in time. Okay. So, which trig function has the O and the H in it? Jeremy. Good. Got it right this time. See? Well done. So I can say this. The sine of 30 equals perpendicular over tension. I want to get perpendicular by itself. Okay, Cormac, how would I get perpendicular by itself? How would I move the T on the bottom over? It's very similar. And as long as they give me the same angle and the same location and the same setup, yeah. But in real life, you know, it's more complicated. But I can plug that in. So here's what I get. I get mass beam times G times 0.41 plus mass of the load times G times 0.82 equals tension sine 30 times 0.82. And again, oh, that's not too bad. Gerard, how would I get the T by itself? How would I move the sine 30 and the 0.82 over? Yeah, I mean, it's a load of work to get there. Think about this massive free body diagram and trig and components. But I always liked these because the punchline was always, tension is going to be, it's going to be a sine 30 on the bottom, a 0.82 on the bottom. Mass of the beam was 0.22 times 9.8 times 0.41 plus mass of the load 0.7 times 9.8 times 0.82. You actually get a pretty clean expression. Finding the tension is actually kind of the easy part. And I think this actually works out to a non-repeating decimal. I think you get like a clean answer to 3 decimal places or something like that. I might be totally wrong, but I think it works out not evenly, because evenly would be no decimals. But you get 15.876, is that right? And no change. 15.876 newtons. And that's good because we're going to be using that for the remainder to do other stuff as well. So I don't have to worry about rounding off. I'll use the whole thing. What's the next thing they asked us to find? The hinge force. Here's what I'm going to do. I'm going to figure out how big Fx is as a number. I'm going to figure out how big Fy is as a number. And I'm going to add them together. Any thoughts on how I might want to add them together? Draw them tip to tail. We're going to do some vector math. So how big is Fx? If I look at my free body diagram, what must it be exactly the same size as? It's got to be the same size as T parallel, because everything right has to equal everything. There's only one left force. There's only one right force, so they have to equal each other. So one of the first things I'm going to say for part B here is T, Mr. Dueck, Fx equals T parallel. Which trig function was T perpendicular? We just did it a few minutes ago. Which trig function was T perpendicular? Which trig function do you think T parallel is going to be? Can you guess? Of course you can. Of course you can. Cosine. Fx is going to be T cos 30. It's going to be 15.876 cos 30. This won't work out evenly, but let's carry a few extra sig figs because we're going to use this. Oh, how about 13.749 and just round to there? There's a 0 after that. 13.749 newtons. Okay? Which way is Fy pointing in my free body diagram? I'm looking for a two-letter word that starts with a U. What we're going to say is everything down has to equal everything. Okay. What's everything down from my free body diagram? Mass of the beam times G and mass of the load times G. That has to equal everything up. There are two forces pointing up in my free body diagram. What are they? T perpendicular and Fy. Fy and T perpendicular. I want to get the Fy by itself, FYI. How would I get the Fy by itself? Subtract what? Okay. Fy is going to end up being mass of the beam G plus mass of the load G minus T perpendicular. Wait. What can I replace T perpendicular with? So you know what? I wrote T perpendicular. I'm going to lightly cross it out, and above it I'm going to say, hey, that's T sine 30. Lots of substitution here. We're going to get Fy equals, what was the mass of the beam? 0.22 times 9.8 plus 0.7 times 9.8 minus 15.876 sine 30. How big is the vertical component of the force from the pivot? This one I think is going to be pretty small, single digits, I think. In fact, I think it's going to be less than 5. Unless I didn't carry a 1 right, I might. 1 point something sounds ballpark to me. 1.078 newtons. That's the upward component. 13.749 is the sideways component. How could I combine those? How might I draw them, pray tell? So it's going to look like this. We have a short upward component of 1.078. We have a long 13 point, what was it, Mr. Dueck? 749. I'd like to find that. How can I find how long this is? Because this is F pivot. How can I figure out how big that is? I'm looking for a word that starts with the letter P and rhymes with Pythagoras. Yeah, Pythagoras again. Hey, we're coming full circle from the very first lesson of the year. It's going to be 1.078 squared, or answer button squared if you got that, plus 13.749 squared. Square root of that. Ah, typo. And I get has a magnitude of 13.8 newtons. That's the magnitude. What about the direction? Theta is going to go down there. Davin, are you ready? Color, 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 color. 13.749, opposite, adjacent, or hypotenuse. Yay! 1.078. Yay! Jeremy, which trig function has the O and the A in it? I think I can. You got this, you got this. Has the O and the A in it? Yes! You were doing that this weekend, maybe. What goes next to the trig function, the mystery angle? That's going to equal 13.749 divided by 1.078. How do I figure out the angle? Hey, I'm going to use my Shift 10 and my Shift Coast button. Format, put the cube away until we're done, please. I know. What do you get? It's going to be probably more than 70 degrees. In fact, it might even be more than 80. What are you getting? 85.5. Now, this angle here is 85.5. Honestly, they would probably want this one here so they could say above the horizontal. Remember how we used to do that? How can I figure out that small angle? 90 minus, so go 90 minus answer button. At 4.5 degrees above the horizontal. That's the pivot force. And that was also some nice review. Now, I'm going to give you some questions to try. This is not homework. However, you can use them to replace another missing assignment if you want. Or you can be working on other missing assignments during class. Very few of you are completely caught up, so I expect to see very few of you staring at those addictive electronic devices. Here's what you can try. We're going to skip this one. We could do it. It's kind of cool. We could do this. It's kind of cool. But I'm actually only going to give you nice, flat, level, no angle stuff. So number one, based on how you answered the thought puzzle, I'm giving you a seesaw question, a teeter-totter question. I'm going to skip 2. 3 is good. This is the diving board question. We did one like that last day if you want to try it. 4 is good. This is really similar to the bridge, the truck that was crossing the bridge. We did one in the notes last day. We're going to skip 5. We're going to skip 6. We're going to skip 7. 7 is nice just because if you're wondering, that's the physics of how a crane system would work to raise and lower a mass, right? But you can try number 8. If you want to, you can use this assignment to substitute for another one.